Okay, perfect. We're live.
All right.
Okay. Yeah, let's see whether we can directly start where we dropped off last week.
Yeah.
Or maybe just one announcement that we will merge some pull requests today and tomorrow for the release on Friday.
Okay.
So if some people maybe can just go through the open pull request and see whether they have some comments. We probably won't merge all of them though, just the small ones, I think. Okay, then I would say we can start. I mean, do you want to share your screen, Giant?
Yeah. Let me share that.
Someone joined. Hello.
Do you see my screen yet?
Not yet. No.
Oh, hold on. I need to...
Hi, everyone.
Hello. So, Giant, I think you don't have Ubuntu, right?
So... no, I have Mac, but I'm gonna have to drop off the call and come back just to.
Yeah. Okay. No problem. No problem.
Yeah. Give me a second. Okay.
Okay. Let's see whether it works now. Yes, that looks better.
Okay. Perfect. Alrighty. So. Yeah. So we were going to cover some of the discussion about shape optimization, optimization refactoring, and yeah, that's going to be the main topic for today. So this is a slide from last time, but we're trying to rework the optimization framework because there's a whole bevy of issues with it. It hasn't been updated for a while. It isn't. It's hard to keep up to date with all the changes in the main code base, and so we're trying to create, and it's also very specific to aerodynamic shape optimizations. Seeing as SU2 can do way more than that, I think it would be remiss if we didn't have a optimization feature that could use all of SU2's features as well. So the idea is to try and make a robust framework that's easy to keep up to date and to have it deal with way more than just shape optimization problems. And improvements along the way would include improving the way design variables are defined so that people can rapidly define new design variables, and other tidbits like that. But needless to say, it would require a fairly large. It would require basically scrapping most of the Python, the Python scripts that we have that don't work in memory, and trying to move everything to the in-memory Python script. These are some of the goals, and this is just taken from a pull request online. So refactor like SU2 Geo, because that does some basic geometry evaluations with calls to C++ functions, which could easily be moved to Python. Right now, it's also extremely specific to airplanes doing wing and fuselage computations, but we want to try and generalize that as well. And yeah, and this is just a sort of list that you can have a look at. This is by no means exhaustive. So, and if you have any suggestions for things to work on, we can have a running list going on on either the Slack channel or the GitHub PR. Yeah. So the basic solution that we're trying to uh, coalesce around is it relies on using the in-memory Python wrapper. This would try and uh, sidestep a lot of the file moving that happens in the Python currently, and it which causes a lot of problems and a lot of confusion in trying to understand how to um, change things, especially if you're trying to add files to drag. So we're going to try and get rid of all of that, all of those issues, and try and use the in-memory Python wrapper so that it doesn't have to write volume and solution files for every single iteration um, when it runs the simulation. And and a lot of this is well, parts of this have been done for um, fluid structure interaction problems, and so we're going to try and follow some of Pedro and Ruben and Tim's lead on that, on um, how to expose a lot of these things to Python and use them through Python, and use Python really as a driver for the simulations, because it makes it a lot more user friendly that way. And so where we left off last time was we decided that the best way to go about refactoring this is to try and go forward and think about what our user interface is going to be at the end of this process. But to do that, I also wanted to first try and get the most general optimization problem definition and see what is the basic requirement for something that for an optimization framework. And on the screen is just is the most basic optimization, constrained optimization problem definition, where you have a function, some objective function f of x, and it's subject to a certain set of inequality constraints g I of x and equality constraints h j of x, and x being a vector of design variables. This could be anything from FFT box control points to Higgs-Henny bumps, or it could even be like inlet pressures and temperatures. It could be, I don't know, like mass flow rate at a I guess I would, yeah, mass flow rate at an inlet or outlet. These are all things we're hoping we can include in the design variable repertoire of this optimization framework. Also, feel free to stop me anytime. Is it still just 5 of us maybe? But okay. Did anyone else join, or is it just?
I don't know.
Okay.
The world is watching. Don't worry.
Okay.
Yeah,
perfect.
we're all here.
Oh great! Oh great! All right. So the most basic requirement to interface with an optimizer, whether it's a off-the-shelf optimizer from SciPy, or we use a wrapper like PyOptSparse or something of that sort, is you need some sort of callable function which takes an input variable, input as design variables, and you can add simulation conditions to that, and outputs either the value or the gradient of a arbitrary objective or constraint function. That's how any of these optimizers, any of the optimizers that we already work with, do their business. And so, sorry. I live right next to to the train tracks, so you might.
It was also going
by every so often, and so. And the other thing that would be nice, I guess it's not a basic requirement, but it would be a requirement for this optimization framework that we're trying to create, is a way to include any arbitrary config option as a design variable. So, I mean, uh, like we don't need to have like linear solver iterations as a design variable, but any sort of marker definition, any sort of simulation condition definition would be great if we can have all of that as a design variable, and uh, generalizing also any other config options that we add later in um, the development process. Anything that is a numerical value can be considered a plausible design variable for the framework.
That would require an automatic way to be built into the C++ part to get derivatives of all those things, presumably.
Oh, okay.
Yes. So I already thought about that a little bit when I was dealing with this with the expression language, that branch that I have open there.
Yeah.
So in theory, we can leverage that because you can expose everything that you have in the config into like the scope of these functions, and then whenever you use some of them in boundary conditions or wherever, then you can get like the correct chain of dependencies.
But don't you need to, but you still need to register those things as inputs, no? As AD inputs, or no?
Yeah, of course. That's still necessary. Yes.
Yeah. That's the automatic bit that I was referring to.
Oh, okay. Yeah.
Because, we probably don't want to do it we don't want to do it as go over the entire config and register everything, right? I mean, that's probably overkill.
Possible, but like you said, the overhead is probably not that big, I guess.
But we would only really need to. So it would be that if it is a design variable, you register it, or register everything from the very beginning.
Yeah, the problem is that sometimes
depends how you want to approach it.
Yeah, sometimes like these variables are used in a pre-processing step, right? For example, when you construct the solver, then it already uses some of the config options. So that also has to be tracked then, and that's complicated. It's easy for boundary conditions and stuff like that.
Okay.
But if you go for something more like involved, that's complicated to track all the dependencies, I think. So we probably have to limit it to some reasonable variables at the beginning.
Yeah, or like groups of options that we can, reasonably do and would reasonably be used, I guess.
Yeah, exactly. So we have to think of some way. But anyway, the framework in this Python thing should include that.
Yeah.
We have to keep that in mind, I think.
Yeah, I think like because the other set of design options that I'm thinking are like diffuser designs or things like that, where you could change boundary conditions and have boundary conditions be design variables in addition to any shape variables that we might want to use. So it would be good to be able to change boundary conditions as design variables as well.
Yeah, and any combination of that, right?
Yeah, exactly.
Like, combination of shape and I don't know whether that makes sense actually, but might.
It might. I mean, we're trying to make this as generalized and as robust as possible, so we should be able to.
It should be able, yeah,
handle all of it. In case someone comes along and wants to design something that way.
People can be very creative, so there's a need at some point for a feature like that.
Yeah. So there were two basic interface types that we had sort of talked about, which is like having to define the optimization problem by writing code, as opposed to defining it through the input text file method that we usually use. These are just a couple of pros and cons that I thought of off the top of my head, and obviously there are way more, but the main thing about writing Python code is easy to manipulate those functions and constraints and design variables, because then you're just working with Python and NumPy, and so it's a lot less involved writing new code. And that would make sort of defining new design variables easier. But then it does require basic Python coding experience, which arguably could be something that everyone has at this point, but it's still a barrier to entry for some users.
I think it's a barrier for most of the people actually.
Oh, yeah.
Use
Yeah.
the code.
Yeah, that's also true. And
we can have kind of a middle ground. You can say that the framework is based entirely on Python, but then if you want to build an extra layer on top, you can still provide an easy shape optimization script that just takes the user config like it does now, and then tries to automate some of the process for a very basic optimization. If someone that has like no experience with Python still wants to run something, we can give it like an extra helper layer.
Yeah, it's something that sort of translates into translates the text file into Python code, so that you don't necessarily need the need Python coding experience. I guess it would be another wrapper.
Yeah, like a setup tool in a way. More, I don't know.
Yeah, that's the thing. So the one thing is that if we make it such that the optimization can be run through Python, and through Python code, then you can just you can create a whole host of helper functions and example functions for if people want to try and do certain cases, certain specific design cases, I guess. And if you want to do something new, then you'd have to dive into the code and try and make some changes. And by that, hopefully you don't have to dive into C++ code, and you can do a lot of it through just the Python interface.
Yeah.
Yeah, I agree.
Yeah. So with the input text file, the pros are obviously no coding experience, and it's how SU2 interfaces currently. So it would be familiar in that sense. Some of the cons, definitions can be sometimes tedious to specify. And we have our option bloat, which is evident in cconfig currently. And arbitrary design variables becomes harder, but I think what Peter mentioned is correct. If we can have as long as uninitiated users can use it through a text file, I think that's a reasonable goal to have, because then anyone who wants to do more can dive into the code if they want, kind of deal. Yeah. So Tim provided a couple of pseudocode. Oh, sorry. The next step to this is just like sort of trying to visualize what the interface looks like. So that starts by just writing some sort of pseudocode that would run how we would want the simulations to be run. So these are some that Tim had included from the last meeting, where you sort of instantiate a solver. You can run it using the geometry. You can just run it using a single command. You get a function value. You get the adjoint solver. Run the adjoint solver, and then you get the gradient. The main idea behind this is that your adjoint solver also, you don't have to run a gradient projection routine that sort of gets done under the hood, and what you get is actual sensitivities out. that the optimizer can directly use. And also, it would be great to be able to just identify arbitrary objective functions using sort of syntax like this, where you have drag at airfoil, or pressure loss at inlet versus outlet, or something of that sort, using some of the expression language things that Tim has been working on already. So this is sort of some sort of pseudocode for what, if I was setting up a Python optimization problem, what I would like to see the interface to be. Obviously this is up for discussion and things like that. But on the left here, you just have the basic workflow of the optimization problem. You define an optimization problem. This would just be a class. Define what sort of solver you want. You add an objective function. Your objective function has to be a callable function. So you just have sort of a callable function that wraps around the solver and gets that value from the run that's already been done. And if a run hasn't been done, then they should sort of initiate a run or something of that sort. Similarly, you add constraints. So you add DVs. You can add an FFT box, and then you can add another design variable span that can sort of work with the FFT box, for example. You set a set of options using a dictionary, and then you just run optimize, and it sort of goes through the simulation that way. And there's a lot of things behind the scene that would be going on behind the scenes, like initiating the solver, running the direct solution, running the adjoint. But I'm sort of trying to abstract away those details in this. On the right are just some of the functions, like objective function, your thickness constraint, or like a variable definition span, which would sort of work in a specific way, altering the span of something using FFT points. So I don't know if this is sort of something that other people imagined or imagined differently. Feel free to chime in.
No, I think that looks very reasonable, actually. I mean, probably the objective function, though, should just, I don't know, there should be some way that we can pass there the design variable, right? So the
yeah, you're right. Design I did sort of, I forgot about the design variables in these functions, but yeah. So yeah.
So at the highest abstraction, essentially, you pass it like an object as a design variable value.
Yeah. So these, I guess these variable definitions would have to happen before you do your objective function, and yeah, your another variable over here, or the in the objective function, would have to be your design variables.
Mm-hmm. Yeah, something like that would be nice to have. Yeah.
Yeah. And there's okay, I'll get to that later. Similarly, an input text file example would be even simpler, where you can just sort of define, okay, objective pressure loss at inlet versus outlet. You have your constraints, and I'm trying to think of like different things that we could do that's not shape optimization. So forgive me if this optimization doesn't really make sense. But you have design variables, and then I want to do away with like the number system in the config file. I think we can just parse text instead, where you define an FFD box as opposed to saying like the number 30. And then you give it a name, you constrain it somehow using some directions. And so this is where the input text file example is a little more difficult, where you can't have, unless it's already defined in Python, you'd have to redefine sort of a span variable, and trying to do that in text would be difficult. But I think going back to what we said, if you just have a wrapper with some of these options, design variables that we create available, then I think we can have a slightly better user experience.
Yeah, I mean, we can limit it. I mean,
Yeah.
That's not a problem, I think.
Yeah. But yeah, so essentially, it like for an uninitiated user, this sort of interface would probably be nice, where you just have objective, constraint, and then design variables, and then you define them in some way that's a little better than what it's done currently. Basically, is my hope.
Mm-hmm. Yeah.
So some pertinent questions that come out of this is what sort of an optimization interface do we want to use? We just use the functions from SciPy right now. There is PyOptSparse, which is something from the Michigan Design Optimization Lab. They've and they've built upon PyOpt, which was another Python class of functions that allowed you to run optimizations.
But it was not continued anymore, right? So from the MDO lab, yes, but the original PyOpt, I think they started developing it at some point.
Yeah, that sort of that stopped getting developed. And so the MDO lab still develops PyOptSparse.
I mean, it looks good. I mean, maybe that's really an option to use that.
Yeah, so the interface is, again, it's similar to like what we would have if we had SciPy. It just needs callable functions. And the MDO lab has so they have a specific arrow optimization and then an arrow structural optimization framework. And I was looking at that a lot for seeing how, because they require you to write Python code to run optimization, basically, similar to what we had earlier. It's a little more rigid in what they do, because they're specifically doing aerodynamic optimizations. And I think we can learn and try and make something, sort of develop that something better, or at least as good as theirs.
Yeah.
And yeah, so PyOptSparse, the additional thing is, if you do have an SNOpt license, you can use PyOptSparse as well, because it supports SNOpt.
What do you mean with the second point there? Have a way to interact with the Python driver?
Oh yeah, so this is something that I was thinking of. That instead of having to write getter functions for the driver, like right now, to get any sort of force coefficient or things of that sort, you have to call a getter function or create a getter function if there isn't one. I was wondering if there was a way to use either like the output structure, the way the output structure works, to just get an arbitrary function that's defined in the field of variables that the history file could have access to. Sorry, that the output could have access to, and getting that from the driver. I think the output is decoupled from the driver, or I can't remember, but
yes, I mean, the goal would be to just get it from the output then.
See, I guess, but I don't want it to be, ideally not have file IO in the middle of that.
Yeah, I mean, we need to expose also, like, either through the driver or the output object itself.
Yeah. So that you can just grab some, like, drag it airfoil or average mass flow rate at the inlet.
Yes, exactly. So it should be through files.
Yeah, and instead of having to define a getter function for all of these values, if you just had something that sort of parsed the usual names and gave you what you needed.
Yeah, exactly. Yeah. So that would be the idea that I have for the output. Same for the objective function, then, of course.
Yeah, that's what I was getting at from here. And it would require something, and since some of these objective functions and constraints can be sort of across modules, like you could have some coming from SU2 Geo, some from SU2 CFD, we'd have to find a way to sort of bridge that gap as well. Because if you're trying to get the thickness at some location, ideally you should be able to do something similar for that.
Yeah, maybe the idea would be to have it in a similar structure, to have some output structure for the geometry, essentially.
Yeah, I think that's a good idea, but it'll take a while. So
I'm currently like restructuring the output a little bit so that we have different modules for all of the different output things that you can have. And maybe there it would be a good place to have also like a module for the geometry, or for some geometrical things where you don't need a solver actually.
Yeah.
So yeah, that we should do that, so that we have like a common structure to get all the different kind of output or objective function values.
Or we just move all of SU2 Geo to Python and just have it use exposed geometry, like an exposed geometry object in C++ to do it.
That would be another option, yeah. I think the question is, like, first of all, how expensive it is.
Mm-hmm.
And then whether we need like some gradients for that or not, right? This is always the problem that we have then. Of course, we can always do finite differences, like, but okay.
Yeah.
We just have to think about it, but
so some things would be a little more expensive, like going through, like making cuts on the like along the geometry, or calculating thickness, and that I think still would need to be done by the C++ code, but a lot of it can be driven through Python, through a Python interface, I think.
Mm-hmm.
Because it calls a handful of grid deformation, geometry, like C geometry functions, and it calls a couple of grid deformation functions to do the finite differencing. But other than that, it is a fairly simple.
The question is, are these like functions in C geometry? So can we just remove them or input them to some other class or stuff like that?
Oh, I think you need. They require the access to a lot of the geometry constructs. But yeah. Well, I guess we'd mentioned about exposing parts of geometry to Python as well.
Yeah, exactly. Yes. Yeah.
So that would be good.
But that really needs like C geometry, so you cannot make it independent of the.
Yeah.
Okay.
It needs C geometry, yeah.
Mm-hmm.
Okay.
Yeah, we can just have it also as a separate, still leave it as a separate part and expose some of the things also in Python then.
Yeah. Okay. And so, and our last point we've already gone over, it's possible to make any arbitrary config option an assigned variable.
Yeah, maybe we should start with boundary conditions and then.
Yeah, I think so. That's a good idea. Yeah. Okay. This is again exposing classes.
I think we should probably start by refactoring the config if you want to do that, because I mean, you definitely don't want to go into the whole logic of which boundary conditions are active and which options should we be registering to then get the derivatives. If we solve the problem of one, accessing the config options through Python in a generic way, kind of, I don't know, with a dictionary or whatever. Maybe something that's not very efficient, but that it would be very easy to expose everything you have in the config to Python. Then it would then it would also be very easy to know that the Python optimization is asking for that, for a particular boundary condition or whatever, an option is asking for an option to be a variable, and then you would know that you would need to register that in kind of a generic way. So you could kind of look at the you could get an optimizer view of the config as just kind of a bunch of variables, and you would not need to know the names of each one of them or the specific functions to access each one of them.
Okay, yeah, but that would mean that we have to do the config restructuring first, right?
I mean, not necessarily first. We don't have to do everything, just because we can't do everything, right? We start with the variables that most people will likely need to use, which will be geometry based, and we just go from there, right? It's
yeah, you're right.
And the discrete adjoint solver already registers a lot of the variables. So, at least Mach number and free stream pressures, temperatures, so on. It already gets derivatives for all of those.
Yeah. Maybe we can restrict it at the beginning to these variables then.
So there's already some variables that could be used as kind of prototype, I guess.
That's a good idea. Okay. This is, again, we're talking about exposing classes to Python, and whether we want to expose entire C++ classes or create wrapper classes that only expose subsets of functions. So far, I think we've been doing the latter, where you have wrapper classes that expose subsets of functions. Is there a reason to do otherwise? Yeah,
I think it still makes sense to have to do it like with special wrapper classes, actually. For example, if you consider the solver, right? Right now in the code we have the output and the solver separate, but actually they should not be. Maybe in the code it is okay, but from the outside, because you want to ask the solver to get some output, right? And not separate like output module.
Yeah.
So in that sense, it would make sense to just combine that in one wrapper class.
Yeah.
But yeah.
Oh, to sort of put together the solver and output structure in one.
Yeah, exactly. Maybe you can combine also other things.
Yeah. Possibly, yeah.
Hey guys, I can add a comment here on from a long time ago when David Thomas was first setting this up. We went back and forth about what level, so how much to expose. So like what was the right level to put into Swig, basically. So we ended up deciding on keeping the Python only one level deep in that it goes to the driver, as you guys have seen. So it basically it'll wrap everything that shows up in the driver, but we didn't want too much manual effort of people going down and writing a ton of these .i files for all of the individual classes. So it was a compromise between, maintainability and then how much we expose. That's just the history of it. We don't have to stick with that, but the decision at the time was made that if you want to expose more things, we have everything in the driver. So just, create new subclasses, put them inside the driver, create new functions, and then it'll be exposed automatically.
So you need for every file you need a separate .i file? Cannot remember how that.
Yeah, it's been a long time since I've done this too, but I think the way it was set up is that the compilation just needs one .i file because we have basically everything inside of the driver. The main just kicks off the driver, and then the driver holds all the data. In that sense, I think we only need one to take care of compiling the driver for Swig, and then any functions that show up inside of driver, that access the data will automatically be populated inside the Python API. So it's just a consideration. I mean, that's why we went with that at the beginning. So just some history. It's not, we don't have to stick with that though.
Yeah, it's a good point actually.
I think that's the best way to do it.
I would be in favor of having like a limited amount of classes, and maybe, like I said, combining them.
Yeah, because we shouldn't need that many just for, to expose things to an optimizer. We shouldn't need that many. And if you give too many options, one, it's harder to document and learn, and starts giving options. It opens opportunities to start using things in a way that will probably not be differentiable anymore.
Yeah.
Because, for example, when you to do a joints of FSI cases in through Python, Ruben needs to manage the adjoints that are being passed around explicitly on the Python side. So it's not completely automated anymore. You need to be more aware of what you're doing, and it's not just a matter of saying run.
Fair.
Yeah, I mean, I agree with keeping the API as small as possible. And so the idea was to have the right level of abstraction. So like at the top level, yeah, you do just want to access things with simple commands like run iteration, output solution, whatever you dream up, but you can write it pretty quickly in the driver level. I don't know that the average person, I don't know how deep the average person wants to get into the solver. Like, I have seen a couple people ask if they could essentially have a routine that would go all the way down into numerics and compute the residual with row or something from Python. But I don't know if that level of detail is where we want to go. I think keeping it pretty high level is ideal for Python.
Yeah. So then the first step would be to figure out what we actually have to expose.
Mm-hmm. So
requires the restructuring in the code.
So it brings us to the next slide, I think, is what I think this was talking about what we will need to sort of expose for the various things. Where I think config structure would be good to expose to Python, just because that's how we interact with the solver in general. Parts
of also the most complicated part, I think.
Yeah, but also the most yeah, for sure. Yeah, it's difficult because that was going to be a tough one, but I think that's a bullet that we have to bite.
Is it even possible to do it in the way that I think of, like having like a C++ structure and then you pass there like another C++ structure? Is that possible in Swig? Probably not, I guess, right?
I'm not sure what you.
Well, so on the pseudocode that I had before, I was writing like you create like a structure and you pass their config, like we do it in C++.
Oh, like here, this?
Yes. I don't think that it is even possible to do it like that, right?
No, it should be possible because you're essentially passing a pointer. And then internal memory of the Swig will provide a C++ object for that pointer.
So passing around pointers is okay?
Yes. So for instance, you, as far as I understood, I'm beginner to all this, but as far as I understood, we can, for example, there is a script in the example for the Python wrapper that you generate MPI structure, and you just pass a pointer of this MPI to the C++ side. So passing pointers in Swig works.
Okay.
I've only done this kind of thing with C types, and the process is similar. Usually, you need to implement some kind of a kind of factory function inside the library you are interfacing with that gives you a pointer back to the Python side. And then anytime you want to, use a method of this object you created, you need to basically pass the pointer back to the C++ side or whatever. So I'm guessing this will be similar.
Mm-hmm. Okay, so that means it works like I had shown there.
Yeah, and I mean this is Python, right? So that config can be a class, then wraps all the whatever crazy things you need to do to make that syntax happen.
Mm-hmm. Yeah. Okay. Yeah. Mm. The question is just whether we need the config or not there. Because, yeah, I don't know. Of course, it would be nice to change some config options in Python, but just to do the optimization, we probably don't need that.
Maybe there is only an essential subset of parameters from config that you need for the entire shape optimization process that you would like to manipulate.
Yeah, if any, right? I don't know whether we really need something from the config.
The only time I've seen it useful is, well, when we're doing multi-point optimizations and you have to define multiple operating conditions. For that case, being able to change config options would be super nice.
I have an example. Python, it's not really pseudocode because it runs, but so I don't know.
Do you want to?
Are you almost done, Giant? Or
yeah, that was my penultimate slide, and the last one is. I actually wasn't sure what the slide was. Tim, this was from your previous presentation.
Yeah, I just thought about some work packages,
Okay.
but it's not up to date anymore.
Yeah. Okay. So I'll just stop sharing. Give me a second. Yeah.
All right. Can you see my screen now?
Of course not.
Oh, come on. I did the whole Ubuntu thing already.
Yeah, but did you restart or did you reconnect to the?
No, I did it before I joined. Are you serious? You can't see my screen?
No. So what did you do last time? Same thing?
I enabled the sharing on the Ubuntu configurations, and yeah, it's telling me that everything is active.
Then try to rejoin.
Do you need to make me presenter, maybe?
No. You're like immediately presenter if you just share.
And nothing shows up now.
Well, it shows the sharing symbol, so like a small screen, but it's not actually sharing something.
Okay.
Yeah, then let's wait a couple of minutes. Yeah, but what I was saying about the config is that you always, if you change something in a config, then you probably have to create a new driver to like do all the pre-processing again. And that's
oh, I see.
That's always the problem that I have with or when I think about it. That
All right, I'm trying again. Does it work?
I would love to say yes, but unfortunately I have to say no. That's unfortunate.
Where is this option usually? I mean, I'm also Ubuntu user, just to know for future.
All right, so when you open settings, you go to sharing, and then you need to turn on sharing, and then screen sharing, you need to turn that on as well.
Okay.
Peter, you could send it to one of us, and we could share our screen.
Okay.
So, Tim, along those lines, would you, if you had to change, if you changed like the free stream Mach number, for example, you would have to, I guess you'd have to run through the driver processing.
You have to create like a new solver, because
Yeah,
the constructor takes all the things from the config.
Yeah.
Like all the free stream things, and yeah.
Okay.
I sent it to you, Tim.
Yeah.
You could open that.
Yes, I can. Just to see.
Also, if anyone has any other examples for how they would like to use an optimization framework that isn't aerodynamic shape optimization, please let me know so I have something to reference when we're trying to create something that's generalized.
Okay. Okay, you just see a black screen, I guess.
Yeah.
What the fuck?
YouTube. Oh, I see a mouse pointer now.
You see a mouse pointer?
Yeah.
Yeah, we see a tiny little pointer.
What the fuck? Always these technical problems here.
Do you have a dual screen? Yeah.
No.
No?
No, I'm on notebook here. It's just I can only share window, separate application windows, but not the full screen. What the fuck? Maybe you should have sent it to someone else.
So you can only share an application window?
Yeah, but only Chrome tabs and Chrome, but not any other application apparently. I don't know why that's the case.
No, you should be able to share. One of the options was just share your screen.
Yeah, but it's just black. Okay, I can share Spider. This okay, that seems to work.
There we go.
Can have it a little bit bigger, I guess.
Yeah.
Okay.
Okay, so without further ado, so this is I mean this is a bit more than pseudocode, because this is what I have right now to run optimizations, and it's all text based. But I mean what I'm interested in is the syntax. So this thing starts with creating design variables, and in this case it's only one design variable, and then there's a few numbers. There's the initial value. There's the size of the variable. So this is a vector with 1600 variables, and then in specifying the variables, I give it scale, lower bound, and upper bound as well. Then I have some parameters, and these are things that I use to just interface with the config file directly to change, for example, the type of objective function that's being evaluated. So that with just one configuration file or with one template configuration file, I change it to evaluate different things. So if you scroll down, please, Tim.
Yeah, where do you want to go?
Functions. We can go straight to functions and yeah. So then I define the functions that I will eventually use in the optimization. So again, this is text-based. So in creating the function, basically the way that the value is obtained is from a file and from a file reader. And then for the functions, I need to add or specify what are the input variables of each function, because functions might have different input variables. So I think that variables need to be attached to specific functions, because not all things will depend on the same set of variables, I guess. And for each variable that I attach to a function, I need to specify a way to read, or in this case read, because again it's all files, to read the gradient. And then also I specify steps to.
Okay, now it's gone, I think.
And so for each function, I specify which steps are required to evaluate the value, and which steps are required to evaluate the gradient. So that's what you see there: add value evaluation step, add gradient evaluation step. And so this, for example, would be to evaluate the value. You would need, for example, in a shape optimization, you would need the deformation. So you would need the deformation, and then to run the primal solver. And to evaluate the gradient, you would need to run the joint solver and potentially the projection step to get the derivatives. And so what I then do, or what I then can do with this is that this evaluation steps are then used to build a graph, and that graph allows then to execute certain things in parallel. So, for example, if you have two operating points, I would like our framework to be able to run those things in parallel if we wanted. Everything that is independent can potentially be launched simultaneously.
But sorry, just to ask, how do you do that then? Because the optimizer is like taking care of calling the different steps, right?
The optimizer is taking care of what?
Of calling the different steps. So how do you make sure that it can run in parallel then?
Exactly. Then comes the last layer of this, which is the driver, and this driver. So I have a family of drivers which I use. One to implement simple methods or simple aggregation methods like the exterior penalty method. That's what is in this example file. And also to interface with different optimizers. So for example, I have this exterior penalty driver exposes some callbacks that naturally interface with the SciPy interface. So that's here in line 88. So you have a method called driver fun for function and driver grad for gradient, and you can pass those things directly to SciPy to run the optimization. But then it's the driver inside that knows how to extract this evaluation parallelization.
Okay.
And the same thing, especially with the adjoints. So for example, if you will usually have multiple constraints at the same operating point. For example, you're minimizing you're minimizing drag, but you have a constraint on lift, you have a constraint on pitching moment, and so on. These three things can be, the adjoints of these three things can be run in parallel as well, or not in parallel, let's say simultaneously, or the computation can be launched simultaneously. And the driver, the optimization driver does this. So it wraps, it creates the callbacks with a signature that is compatible with the particular optimizer that we want to use, be that from SciPy or from somewhere else. And it enables this kind of parallelization, if you want. And it also does, so based on all these things, it also does lazy evaluation of some things. So for example, if some constraint is not active, it doesn't, and we know that the optimizer supports this or is okay with this assumption. If a constraint is not active, we don't compute the gradient, for example, or things like this.
Okay. So that's all in this driver thing that you have there?
Yeah.
Okay.
Yeah.
And you wrote, that's your implementation?
Yeah. Yeah.
Well, I mean, I guess we could like incorporate that somehow. Should be possible, right?
Yeah, and the syntax to add, objectives and constraints is it's exactly like what Giant was showing. So you just do add objective, and you can add as many objectives as you want, and then usually they just need to be combined with some weights. And then you can add upper bounds, lower bounds, and this takes care of so you add the function that you want to, you add the function and you add the bound, and then the driver takes care of doing the shifting, because for example in SciPy, when you use constraints in SciPy, the bound needs to be 0. For equality or inequality, the bound is always assumed to be 0. And so this takes care of doing the shifting of the function without needing the user to type extra code to do this.
Mm-hmm. Mm-hmm.
Yeah, so this is, you're right. This is approximately what I was imagining when I was writing that Python pseudocode.
Yeah, and then the question is whether we can combine that with PyOptSparse. I guess so, right?
Yeah, I mean, there might be some changes in the exact passing of things, but yeah, it should really be quite similar.
Yeah, right now I have this this thing that naturally goes into SciPy, naturally connects with SciPy, and I have a driver for IP-opt as well.
Yeah, hopefully you only need one then. If we use PyOptSparse, I guess they all have the same signature, I assume.
Yeah, probably. Yeah.
But I mean, this is just the second step then, essentially, right? Because it should be easy, or the goal would be to easily like change the optimizer anyway. Yeah. Yeah, but it's good that you have some base implementation. Maybe we can really leverage on that.
Yeah, I think that's a good idea. It's somewhere to start. Yeah. The question is just, like you like you said, where to start exactly, right? Yeah.
Because first, I think the problem is also to define what we need. We have to expose. Maybe we can just start with a limited amount of things that we expose.
Yeah.
Oh.
think starting with I guess the best way would be to try and replicate what we have right now in this new framework to begin with. So that means having a couple of design variables, mostly geometry based. No, actually, almost all geometry based, and then try and bring in these different parts as we need them to. So, for example, once we have a framework that works in this sort of way, where you can add objectives and things like that, that way we can at least have something that replicates the current functionality, test that, then move ahead to, for example, changing config structures or changing how FFD boxes are handled. Those are all things that can go on either after or concurrently, I guess, but depends on how many people have how many man hours to put into this.
Yeah, so maybe we have to define what I had also on this other slide. There are some work packages that can run
right
concurrently, so that people know where they can work on if they want to work on something.
Yeah, so I guess should we then start defining some of the details of what needs to be?
Yeah, that would be good, I think. So we have to be a little bit concrete.
Yeah, or at least sort of try and group them into things, and then people can volunteer on parts and projects that they want to volunteer for.
Yeah, that would be good, I think, if we do that. So someone has an idea how to do that?
I mean, I can create some sort of overarching groups of things, groups of work thrusts that would be required, like config restructuring, optimization restructuring, FFD extraction from C++, or I mean, I can create those, and then people could volunteer for different things.
Yeah, maybe you start with the skeleton, and then we can fill it, I think.
Yeah.
That would be good, I think. Because we have a couple of things that we have to do.
Yeah. We wouldn't necessarily be the best thing to do live on this, but I can do it after the meeting.
Yeah, that's okay. That's okay.
Yeah.
That if you like this kind of or if you're not too bothered by this kind of setup, this methods of basically the bit of obtaining, reading the value of the functions would be just a matter of, well, not just, but it would require exposing or allowing some interfacing with the output structure, which is what you're working on, and then the different evaluation steps for the direct problem and the adjoint problem. If you scroll up a bit on that file, is just basically exposing the basic functionality. So one is running SU2 CFD, and the other one is running CFD AD. I don't know, because some of these things I think, I don't know. I think this kind of separation between just the different, just running the code and getting the values, I think needs to be kind of separate, because you can you can run the code once and extract multiple outputs from the same run.
Yep.
And the same way, I don't know if you define just one big abstraction, which is let's say function. You would probably need to put into the function all the geometry deformation and so on, and it would be more difficult to make sure that you only do the deformation once, for example, which should be possible. You should only need to deform to do the deformation step once, and then evaluate everything you want on just that one geometry.
You could make it dependent on the design variable value, I guess.
Yeah, if the values don't change, you don't run it again. Yeah.
Yeah, that's what is currently done in the framework, I think. But yeah, I mean, I like the structure. So in the end, we just have to replace the
text files by Python objects that directly call SU2, basically.
Yes, exactly. Yeah. Maybe from that we can also see what we actually have to expose and what we or at least what we have to expose at the beginning.
Yeah.
Like I said, maybe not exposing the output directly, but having it through some combined structure with the solver. Or maybe we don't need the solver at all, actually. I don't know. I have to think about it. Okay, some other ideas?
If not, it might be a good place to stop because we're past the hour, and then we can move on to
Yeah, that's fine for me.
next steps.
Yeah. Pedro, can you share these things somehow?
It's on my GitHub.
Okay, perfect. I mean, if then maybe you could just post the link in the Slack channel or something like that, if it is public. If you want to make it public.
No, it's already public, and it has a license. It's the same as SU2. So.
Okay, perfect. Yeah, then just share the link, and then we can all have a look and see.
Yeah, I'll put it in the refactor optimization channel.
Okay, perfect. Okay, yeah. From my side, we can leave it like that at the moment.
Yeah.
We define the work packages.
Mm-hmm.
Maybe you could just open a Google Doc or something like that for that.
Yeah, I'll do something of that sort. Try and organize as much as I can and create some initial subtasks, just so people have an idea of what kind of work needs to be done.
Mm-hmm. Okay.
All right.
Then I would say we do it like that. Just one quick thing about the pull request. So the pull request that we want to merge in for Friday. So is there any pull request that we have to still merge in that we want to integrate for the next version? Probably Pedro, from you, there's one, I guess.
Yeah, I have one more I can merge, yeah, and there's Clark's one with the shape optimization restart.
Yeah.
Oh yeah, we can merge that one in and the unit testing also, because the case should have passed by now. Yes, okay. So your pull request would be the arrow thermoelasticity, or which one do you want to?
Yeah, that's the one.
Okay. Then I'm going to look at this one later. I think, yeah, Tom's also, we can probably merge it in soon, I guess. I mean, I don't see a reason why not. But that should be it, I guess, right?
Okay.
Yeah, I think for now.
Okay, perfect. Then okay, perfect. Then we do it like that.
Yeah.
And I will probably create the release on Friday, I guess. But that should be fine, I think, although it's not April anymore. But okay, then. And yeah, let's see what we can come up with.
All right. See you guys
Bye bye.
next week.
Yeah.
Bye bye.